Okay, good morning. Just a quick run through of a little activity I'm going to have you go through today to reinforce the concepts you saw uh, in the investigations you did the last couple of days. Obviously, it's going to be important that you ask a lot of questions. Theoretically, you've seen most of what you needed to see. I'm going to click on this thing now. It might take a second to load. And basically, this will give you a chance to kind of run through it, test some of some of what you've seen, and hopefully go back and verify when you find that you don't have as good an idea about something as maybe you hopefully would. It may be a little slow to load. Give it a second. Obviously, the busier it is. Right now, it's pretty early in the morning, so it's not too busy, but later on, it might be a little bit slower. So you get here, click Start. Pretty simple. A little bit of description here. If you go into the tutorial, just sort of quick comments here. The first thing it talks about is function notation. You've seen function notation in the past, probably in both the MCR and the MCF classes, grade 11. Just f at x, g at x, anything that looks like that, you want to remember is exactly the same as y. And it functions exactly the same as y. There's really no difference there for your purposes. Intercepts, we haven't spoken of the y-intercept specifically yet. I guess we haven't spoken about the x-intercept too much either. Again, x and y-intercepts, just where we cross the axes. So the x-intercept is where we cross the x-line, the horizontal line. The y-intercept is where we cross the y-axis, the vertical line. Odd or even, this is one of the sections I don't necessarily think is important. Odd functions have exponents that are odd numbers. In this case, the 5 is the biggest one, so it has a degree of 5, which means it's an odd degree. This one's an even degree because it's got an, I hope you can see actually the mouse on the screen, but the 3x squared minus 4x plus 17 is an even degree because it has a 2 there as the highest degree. And positive or negative, when we talk about this, it's just asking about the very first number, the leading coefficient. I think we've talked about that a little bit in the last couple of days. So it's just asking you, is it a positive or negative number? Pretty straightforward stuff. The thing I don't like about that, and I might have mentioned it in the last video, is I don't want you trying to memorize what a positive coefficient with an even degree function does. I want you to be able to think about what happens at the end values by plugging in numbers. So this is really where we get to. I can't actually show you here. I'm going to pull this up and set for a second. Okay, so this is again just kind of a summary of what goes on, but I don't really want you trying to memorize that. What I want you to be able to do is look at a function, plug in some numbers, and decide where am I, what's going on. So in case you don't remember, that wasn't very good. When we're talking about quadrants, this is quadrant 1, 2, 3, and 4. And so if I have a graph that looks something like this, which hopefully you remember is cubic, it starts in quadrant 3, goes to quadrant 1. So it's going to look something like this perhaps. How do I know that it's, sort of the question is basically what's going on here? Is it positive or negative? And again, all I have to do is try some numbers. So if x is something like negative 1,000 or negative 10,000, then I get x cubed is going to be negative 1,000 cubed, which is to say it's negative. And so down here, as x goes that way, the graph goes that way. Same sort of idea on the other end over here. Try some values like as x is approaching 1,000, 10,000, 1,000,000, whatever. I'm getting x cubed, continuing on to the positive values, and so I know that it's going to go up that way. I'm not multiplying by anything out front in this spot specifically, and so my negative values will stay negative, my positive values will stay positive. So you're going to get a chance to play with this a little bit here. So this is just, again, the tutorial. It's kind of a note and not really that important. This is sort of the one thing that will be new to you. When you look at something like, oh, I can't draw on that, sorry. When you look at something like this with the y equals x plus 1 squared part, what it does is it tells us sort of where the zeros of the expression are. And so, again, can't see my hand. Oh, look at that. Something showed up on the screen. Right there, that's the spot x is negative 1. And so from the term x plus 1 here, I can determine that at negative 1, the value that makes this thing go to 0 is where my zeros will occur. Okay, so I'll sort of pop one of these up, I guess, because I thought I could do it on there. So, oh, I seem to have lost. No, I did not. So if I just look at a simple graph like this, these key points here are what we call the zeros of the expression. And if we just assume that these are sort of fairly evenly spaced, 1, 2, 3, 4, 5, 6, 1, 2, 3, and negative 4, it means that those terms, or sorry, in my expression, I will have these values. So my equation will at least have those things. It may have something else in this spot. In fact, it will. I'll sort of mention that quickly in a second. But basically what we see is that because when x is negative 4, this term becomes a 0, then it means that all of the terms would multiply out to 0, and this x minus 4 helps me establish that this is one of the factors of my expression. The opposite is true for the other values, or the same, I suppose you could say, is true for the other values, in that when I put a 1 into the expression, it has to give me an answer of y being 0. And so right here, when I plug the 1 in, this becomes 0, and the other values will multiply out to 0. So this is sort of the zeros here at negative 4, positive 1, and at 6 help me establish, again, these three pieces of my expression. The one thing that is missing here is understanding that there's going to actually be a negative in here. Leave myself a lot of room. I'm going to have a negative value here. And I know that because when x is very small, or sorry, when x is approaching the, again, the negative 10,000s, negative 100,000s, and so on, if they have just an x cubed term, that would end up going towards a negative infinity. But on my graph up here, I clearly see I should be going towards the positive, so I actually need a negative in front to ensure that I'm going to positive infinity. Okay, so that's sort of how I determine whether there's going to be a negative coefficient there or not. Basically, do I need it, yes or no? Now the last thing, and you'll see this, you know, again, you're going to have time to practice these, so although it's maybe not super clear right now, please know that you know, your job today will basically be to play with this interactive activity and kind of get a feel for what's going on. Slightly different example now. Okay. So if I have something like this, the big key is understanding that here Of course, here and here as well, I've got zeros. But in this case, for the first time I've seen, my graph does not go through the x-axis, but actually bounces back off. And what that's going to tell me is that the factors I have, I've still got my, let's see, -1, 2, 3, my -5 over here, let's say, and my +2 over here. So I'm going to have my x plus 5 to deal with the -5, my x plus 1 to deal with the -1. I'm going to have an x minus 2 to deal with the +2. But the fact that what I've got here is kind of a little parabola tells me that I must have actually had that section of the graph be a quadratic, or parabola itself. So this by itself, if you graphed it, would be a parabola. So it actually makes a little parabola on my graph. Having said that, you can probably guess what would happen if I did kind of continue this graph out and say, oh, wait a minute, what if it came back down one more time and did something like, not like that at all, did something like, wow, I can't draw it. That's a little bit better. What if it did something like this on the endpoint where, it's still not very good. Okay. So we'll go with that. So what if there was another value out here that we kind of went through in a little bit of a different way, where it sort of comes up, bends through, and then continues on back to the rest of the graph. That section of the graph itself is what we typically see as being a cubic function, something like x cubed, other than this little tip here. And so what that means is if I did continue this out to -6, -7, -8, -9, if I've got that basic cubic shape on the end, then what I have to have is on the end, I've got an x, that's supposed to be an x plus 9 to the exponent 3 as well. Okay, so sorry, that was kind of poorly done. I thought I knew where I was going and I kind of got hung up. But the basic idea is whenever you see a factor, you're going to be going to, you're going to hit that spot, you're going to hit that 0 on the graph, with your graph. If it happens to be a linear 0, meaning there's just an exponent of 1 on those, or you don't write 1 in, the graph will go straight through, like a straight line would. If you have a square on it, the graph will be parabolic at that exact spot, so kind of bounce off it the way the second exponent did. If you have a exponent 3 at that spot, you'll get kind of a cubic move through that 0. Okay. So, not a great finish to the video, but I think that's kind of established what you will need to see. The big thing here is when you're running through this, it's going to quiz you, just going to skip a couple questions here. Okay, so something like this, basically what it's asking me to do is write down the information. This has, excuse me, 2 bends in it, so I should be recognizing that as being cubic. So if it's cubic, that means it's something like x cubed. But if x cubed had large negative values, then it would normally come up from down here and go this way, which means that the coefficient at the start must be negative to switch that. I have 1, 2, 3 zeros. I have no double roots. Double roots would be things like the x squared we just talked about, where my graph would make a parabola at that specific spot on that 0. And triple roots would be spots where I kind of pass through the 0 but make this basic cubic shape as well. There are none of those. Where does it start? Starting quadrant, it's starting up here. Our numbers are 1, 2, 3, 4. So it's starting in quadrant 2, it's ending in quadrant 4. Submit, and it gives me little check marks to let me know what I'm doing. So some of this is definition, basically making sure you recognize what your quadrants are, making sure you recognize from the graph what's going on here. Certainly the least important part, probably the positive negatives here, because it's something that once you have the equation, you'll work out. Let's see if we just find a couple here that are decent to look at. Okay, so this one, it might be a little tough to tell, but I think what I've got, as I'm coming down here, I've got 1 bend, 2 bend, 3, 4. So 4 changes of direction means that I have a quintic function. You're not expected to know that, other than to know that every time it bends, I have 1 higher exponent. So a linear equation, linear function has 0 bends, 0 turns, because it's straight. A quadratic, power 2, has 1 turn. Cubic, power 3, has 2 turns, and so on. Same sort of idea now. If the exponent is 5, normally a negative number would make me a negative y value. A negative x value would give me a negative y value. So that means basically I've got the opposite of that. Zeros, it looks like 1, 2, 3, 4 to me. Double roots, I'm hoping this is a double root in this one spot right here. I don't see any triple roots. And again, starts in quadrant 2, ends in quadrant 4. Number of zeros is not 4, so 1, 2, 3, 4, 5. I guess this is kind of going through. No, it's not, because it's a double root there. Oh, okay, sorry. My fault. There are 5 roots is what it's saying. But, okay, so that's good to know. So what it's telling me is the double root actually counts as 2 roots. So I have 1, 2, 3, 4. This double root is counted twice. That's why it's called a double root, I guess. I guess. And this one here. So there's 4 distinct zeros, but for the purpose of the quiz, one of them is used twice, so there are 5 altogether. Okay, so I'm going to stop there. I've gone way too long. Play with this, get used to it, ask lots of questions. Tomorrow we'll be graphing some of these on our own. Maybe I'll put some up today, but I'm not too sure.